Hi, my name is Sheynik, so I suppose I should clarify with respect to Gal's problem. I did offer some cash prize. I don't remember how much it was. 100. No, I don't think so. But we can make it 50 rei for the duration of this workshop. One could add incentives and bonuses, I suppose. But so, my name is Sheynik. Ich bin ein Berliner. And the problem I'd like to pose is an example of what's called an Erdős-Rothschild problem. So I'll first explain what the problem is in general, and this goes back to the roots. So if we look at triangle freeness, then there's the natural extremal problem, which is otherwise known as Mantel's problem. How many edges can an n-vertex graph have without having a triangle? Okay, and then we all know the answer is n squared over 4 with the complete bipartite graph. Then there's a Ramsey type problem. And I suppose this is really an inverse Ramsey problem. It's asking how many colors do you need to color the edges of the complete graph without a monochromatic triangle? Okay, and so we can combine these two problems in some sense to get the ER problem, named after Erdős and Rothschild, and that's asking a sort of combination. Instead of maximizing the size of the graph, we want to maximize the number of colorings which avoid a monochromatic triangle. And so when I say colorings, we fix the number of colors. Okay, so there's a clear lower bound here. If you start with a triangle-free graph, then any edge coloring will be triangle-free and therefore monochromatic triangle-free, so you can certainly get r to the n squared over 4. And in fact, Erdős and Rothschild conjectured that this was correct when r is equal to 2. This was proven by Euster, and then Alon, Balog, Kivesh, and Sudakov, if I remember correctly, showed that was true for r equals 3 as well, and also for larger cliques, you would take the corresponding Turan graph there. Okay, but it turns out that for R4 or larger, this lower bound is not correct. Let's say this is the right bound. And when R is larger, we know very little about this problem. I think that's fair to say. So if r is equal to 4, then for this monochromatic triangle-free graph, we know the answer. That was work of Pikurko and Yilma. And I think for r equals 4 and monochromatic K4 free graphs, we also know the answer. But apart from that, I don't know any pair where the answer is known. So by pair, I mean a number of colors, which is at least 4, and the size of the monochromatic clique, which is forbidden. Okay, so this is a problem which one could solve. That would be quite challenging, probably. I guess there's some more recent work of Pikurko, Steden, and Yilma, where they look at this problem. They generalize it, so for each different color, you can forbid a different clique size that's monochromatic in that color, and then they reduce that in general to some optimization problem. Okay, so if you could solve that optimization problem, you would get a log asymptotic answer for the number of colorings you could have. Okay, but that optimization problem is a very large optimization problem, depending on the Ramsey number, the multicolor Ramsey numbers here. Okay, so it's not feasible to solve that in practice. Okay, so perhaps some additional ideas are needed to try and approach this. But for something which should be achievable, hopefully during this week, this is a variation I've been thinking about for a while and been a bit stuck on. So you could ask this kind of problem for any extremal problem. Okay, so instead of looking at triangle-free graphs, an extremal problem, you want to forbid some sort of structure, and now you want to color the elements and maximize the number of colorings without monochromatic forbidden structures. And so the one I'd be interested in is the version of the Erdős problem. So the Erdős theorem is an extremal result which says if you have any sequence of length k squared plus 1 of natural numbers, then you'll find a monochromatic sequence of length k plus 1. I apologize for my handwriting in advance. Or not in advance, I suppose. Okay, and this bound is tight, so you can construct what I'll call Erdős sequences of length k squared, which do not contain any monochromatic sequence of length k plus 1. So what do they look like? You take, for example, k increasing sequences of length k, and you arrange them in a decreasing fashion. And so now the question is, what if we color the elements of the sequences, and we want to avoid not just a monotone sequence, but a monochromatic monotone sequence? Okay, so again, obviously, if you took one of these sequences, you could color it arbitrarily. You'd get 2 to the k squared. Again, in most other Erdős-Rothschild problems, that is the correct answer. You take the extremal solution, and then you take all colorings of that. Okay, but here it turns out you can do better. So you can modify this Erdős sequence by making these subsequences longer. And you'll still have k sequences. And now in each subsequence, you color half the elements red and half the elements blue. Again, you can do this arbitrarily for each subsequence. Then when you look at each color class, you'll see one of the Erdős sequences. Okay, and so they will be k+1 monotone sequence free. Okay, so how many colorings does that give you? You have 2k, choose k, choices for each sequence, and you have to color k sequences this way, and so that is going to be two to the 2k squared, approximately, instead of the 2 to the k squared from the trivial construction. Okay, and you can show that log asymptotically this is the best possible, because if your sequence has more than 2k squared elements to begin with, then in any two coloring, one of the larger color class will have more than k squared elements, and therefore by Erdős-Sekkeres, a monotone sequence of length k+1. Okay, but I believe that this should really be the correct answer. Okay, exactly. So question. Okay, so can you do better than exactly this number here? Okay, and then of course you can generalize this to having more than two colors. You could have R colors instead, and then you have here a multinomial coefficient instead. That I'm not so convinced about whether that should be best possible, but for two colors I can't see anything better. Okay, so thanks. Any questions about the problem? Yeah. So the upper bound is 2 to the 2k squared is an upper bound you can give, because if your sequence had more than 2k squared elements, then in any two coloring, the larger color class has more than k squared. You can be a little cleverer and get 2k squared, choose k squared, because if you really had your 2k squared, each color class has size at most k squared, so you get this instead. Okay, which is, of course, a bit less than that, but log asymptotically, these are all the same. So here it's really about getting the precise answer if possible. And this is maybe related to some of the supersaturation problems for monotone sequences which have been studied recently. And there the supersaturation phenomenon is typically weaker than in the graph setting, which maybe explains here why for two colors we can do better than the trivial construction.